Good morning. I will start the session 10A. My name is Jožef Lithuania. I'm coming from Slovenia, from University of Maribor, Faculty of Electrical Engineering and Computer Science. In this session, we will have contribution from the area of electrical engineering. There are 6 contributions. All presenters are here. It means we will start now at 9:30 and we will finish at 11. So every contributors will have approximately 15 minutes. So if it is possible, I ask you not to exceed the limitation. So if you agree, I suggest that we will start. Our first presenter will come from Poland, from Gdańsk. This is the paper in the area of synchronous machine and control systems. The title of the paper is Improving Control Dynamics of Permanent Magnetic Synchronous Machine Drive. There are 3 authors, and the presenter is Mr. Leszek Jarzekovic. Please.
Good morning to everyone. Thank you, Mr. Chairman, for introducing myself. There is a little mistake in conference program. Only the first part of the title is there, but the full title is Improving Control Dynamics of PMSM Drive by Estimating Zero Delay Current Value. Dynamic properties are crucial to many applications. In such cases, typically the solutions are fitted with PMSM motors due to their good dynamic performance. Moreover, we can distinguish different kinds of drives. Some are torque control, and their control algorithms consist only of one control loop. This is a current control loop. There are also speed or position control drives, which contains also outer control loops for controlling speed and position. However, in all those cases, the properties of the most inner control loop, that is current control loop, is ultimately limits the performance of outer loops. Therefore, the inner loop is considered as the most important. And although there are numerous papers on some sophisticated control algorithms involving some expert maths and so on, still typical PI controller is very highly appreciated in most of the solutions. So those facts motivated us to propose a solution which enhances the capabilities of typical PI controller by estimating motor current values for the beginning of the forthcoming control cycle. It's something connected to predictive control, but very simple predictive control. And this solution allows us to significantly increase dynamic properties of current control in PMSM drive. Here's a typical structure of field-oriented control applied to PMSM drive. Here's inverter, motor. Some values are measured by digital controllers. They are DC voltage, motor phase currents, and rotor position and speed. Phase currents are transformed into DQ coordinates in order to enable the controller to easily control motor's torque. So we have to control 2 current components. D component is usually forced to 0, and Q component is set accordingly to desired torque. And if we consider the fact that this algorithm is implemented in digital controller, we have to take into consideration that this algorithm operates on the basis of sample and held values, and it is able to update the PWM modulator only once per control cycle. So this somehow limits the performance of such algorithm in digital implementation. So here are some selected waveforms from such drive. At the bottom there is a PWM carrier, a triangle wave, which allows us to set the instance of inverter transistor switchings. In the middle with blue color there is a selected motor voltage, one of the three voltages. Voltages are modulated by inverter, so they change a couple times during control period, during control cycle, but the voltage is modulated in a way that its mean value equals reference value, so the one which is marked in green. And at the top there is a selected current waveform. Current waveforms, motor current waveforms consist of a significant ripple component caused by changes in supplying voltage, and the frequency of those ripples is much higher than control bandwidth. Therefore, control algorithms aims to control only so-called fundamental component of these currents, the one which is marked in green. So the controller needs to extract this fundamental component in order to provide current controllers with proper feedback. And a convenient solution to that was presented some years ago. It's called synchronous sampling, and it uses the fact that current instantaneous values, instantaneous waveform crosses the fundamental component line in the middle and at the beginning of control cycle. So if we sample current at those instants, we obtain fundamental current components. And if we consider some single control cycle, we need to set up a PWM generator before this cycle starts, so before this instant. So we cannot use this current sample to feed control algorithm because we wouldn't have any time to perform computations. So we have no choice, and we pick this or this sample as an input to control algorithm, and we update the PWM generator at this instance. So there is a delay between measurement and updating the generator. And this degrades the dynamic performance of such control loop. So the paper investigates how choosing the instant this or this influences control dynamics. Moreover, we propose to estimate the value at the end of the control cycle, this value, by measuring those two both values here. And we also investigate how such estimation, how such prediction influences control dynamics. So first approach was to perform some simulation. We've developed a model in MATLAB Simulink which represents all those digital phenomena, digital control phenomena, but there is no inverter in this model because we wanted it to represent only fundamental current component. No ripples are involved, and some outcomes are here. Here we have a triangle wave of PWM carrier and a step command, command of Q current component. This is torque producing component, and three responses to this command in blue, green and red color. The blue one represents the case when a current sampling is performed at the beginning of a control cycle. The green one represents the case of measuring the current in the middle of control cycles, and the red one is our proposed case of estimating so-called zero delay current value, so estimating the value at the end of analyzed control cycle. For each of those cases, controller gains were selected individually to obtain 5% gain to be able to compare those cases. And as you can see, by estimating zero current delay, we can effectively increase the response rate of drive. The rise time of this current is approximately 3 times shorter than the blue case and 5.5 shorter than the green case. So it is much faster than standard approaches. So we came to a conclusion: if our approach enables us to obtain such fast response, so we asked ourselves, is it possible to select such controller gain that will enable to obtain single control cycle response and simultaneously no overshoot? And we derived some equations which allowed us to take into consideration motor parameters and control cycle duration. I don't show you these equations here, but the paper is already published and available online, so I encourage you to look in the paper. But I show you only the results. Here is some tests for standstill, where the current changes after a comment, after a step comment changes from 0 to the rated value in a single control cycle. Here's a singular case, but it's on the move, so the rotor is moving with a speed of 25% of the rated value. So the voltage is needed to cancel EMF force, but still our advised gain allows the controller to achieve one control step long response. And the last case is a case of quite high speed. It's half of the rated value. In such a case, the voltage needed to force the current to change to the desired value is higher than inverter output maximal voltage, so it's limited. In such a case, it takes longer than one cycle to obtain the desired response, but it's still technically the shortest possible time to obtain this. And here are some experimental validation results, some oscilloscope recorded waveforms. The one at the top is the most important. It's the IQ current, so the current components which is connected to torque production. And 100 microseconds, it's the duration of control cycle in our case, in our laboratory stand. And 10 amps is a rated value. And following a step command, the IQ current follows the command in one cycle. So in one cycle, the current fundamental component marked in red changes from 0 to the rated value. So we achieved our goal. And some conclusions. Our solution is very simple to implement. It's only marginally increase the computational complexity of control algorithms. In our case, it takes only 6 clock cycles to estimate zero delay control value, so it is about 0.1% of total computation time to involve this upgrade in control system. Although it significantly improves control dynamics. So we have high gain with very insignificant effort. Our approach does not require any hardware changes, although it requires increasing current sampling frequency with a factor of 2, but it's easily achievable on modern digital signal processors. And this solution obtains allows the controller to achieve the fastest technically possible response over step command. And that's all. Thank you for your attention.
So thank you for your presentation. Questions?
Just one question. The sampling time of your control, it's 100 microseconds? Or?
Yes, we have 10 kilohertz modulation frequency. So we sample current, but we sample current twice in each period. So it's 12, not 12, 20 kilohertz something.
Could you explain in short words your experimental system?
Our
The size of synchronous machine and equipment?
Our experimental system was of a power approximately equal to 2 kilowatts, and it was controlled by digital signal processor, 32-bit processor of Texas Instruments, fixed point, and what's to say more? And we had interior permanent magnet synchronous motor of such power rating.
Thank you. So our next presenter came from Pilsen, from University of West Bohemia, Mr. Jan Stepanek, and his contribution is in the area of traction of vehicle tractions.
Good morning, gentlemen. Thank you for my introducing German. My presentation is about cost-effective solution of input voltage stabilizer of auxiliary drive converters for traction vehicles. Now let me give you overview of the I'm going to talk about.
This one, yes,
The other way is backwards, forwards, and laser pointer.
Yeah. My presentation divided to these 5 parts: motivation, auxiliary drives, the new converter concept of voltage input stabilizer, hardware prototypes, and the end is conclusion. And this research has been motivated by our industrial partner with the aim of developing new generation of equipment for light traction vehicles. For our research has been main aim is these parts: high efficiency, high switching frequency for reducing size and weight for passive components. Output power for converter is 22 kilowatts. Operating voltage range is 400 volts to 950 volts for DC catenary. Lifetime F, of course, low cost. The auxiliary drive has great importance for vehicle safety. This block presents a simple topology providing a galvanic isolation between catenary and auxiliary drives. Potentials and importantly protect 2 passengers in these vehicles. This is galvanic isolation. This is battery charger for onboard battery. The auxiliary drives are integrated of part of light traction vehicle. They are mostly used for generating a standard power grid which supplies on board equipment on the top vehicle. This is box for auxiliary drives and traction converter. This is commonly used composed concept of auxiliary drive. This is block of input voltage stabilizer or connection to DC catenary voltage. This is old concept. Main drawback is they using 70-100 volts semiconductors with lower switching frequency, around 8 kHz, higher switching losses, and exactly higher price. Only advantages for this concept is one fire source inverter with 20-100 volts semiconductors. This is novel proposal converter concept of auxiliary drives. This put converter based on serial combination. Two bucks enable using 20,000 volts semiconductors. The input voltage stabilizer converter is supposed input to catenary voltage to e.g. 380 volts DC. Main benefits for this auxiliary drive is high efficiency, reliability, lifetime, low price, reduced size and weight passive components. Advantages for this topology is using 20 volt semiconductors in input voltage stabilizer, high switching frequency, elimination of passive components, size, lower switching losses, and low price. Disadvantages is serial connections of two input converters and higher number of semiconductors in input voltage stabilizer. This table comparison existing concept and new concept. It was a concept to reduce price by 13%. This is summarized. Size by 7% and weight by 15%. This is a hardware prototype for new input voltage stabilizer. New input voltage stabilizer consists of two modules. In this figure is one module, is a 3D module from Altium Designer. This is basic parameters for input voltage stabilizer. This schematic is a power circuit for this prototype. This is one section and two sections. Each switch is composed of three parallel components, three IGBTs without anti-parallel diode and SIC anti-parallel diode. This is this is testing and measurement results. This is converter startup waveform, shows balancing without force ambivalence. This is force ambivalence. There is major ambivalence. It is caused by asymmetrical of both sections involving capacitors C1 and C2 parameters, maybe tuning gate, drive pulse, and other parasitic influences in transistors. This is shows from balancing capacitor with force ambivalence. Ambivalence is made by external resistors. The waveform confirms proper function of balancing controls algorithm of EVS converters. This is balancing states. The slide shows measurements in steady state condition. This is normal function mode. This figure shows input voltage step change in this value to this value, and load step change from 5 kilowatts to 10 kilowatts. The attention was also paid to efficiency measurement, as the losses may limit practical applications to do on the unacceptable temperature rise of the discrete semiconductors device. In this figure illustrated the efficiency curve for the nominal voltage, voltage in and efficiency of over 97% is keep with the output power 2 kilowatts up to approximately 20 kilowatts. This figure, the influences of input voltage stabilizer efficiency documented in this figure, which also validate the proper function of the converter over the whole involved voltage range. It confirms of domain of switching losses, conductive losses at the values decrease with increasing input voltage. This is dominant switching losses in this area. And conclusion, the results provide the employing the latest generation of semiconductors device in a cost-effective discrete package, also the design of an input voltage stabilizer converter with an output power of 22 kilowatts, the capability of reliable operation with the full range of catenary voltage fluctuation 4000 volt DC to 9050 volt DC, achievement switching frequency up to 13 kilohertz. Likewise promise the better passive component optimization in comparison with concept with 1700 volts devices. The overall efficiency of laboratory prototype, which varies between 97% and 98% under almost all input voltage and load condition, promise feasibility design for industrial application. The new input voltage stabilizer concept reduced price by 13%, size by 7%, and finally the weight by 15%. This is comparison for parts of auxiliary drive. Existing concept use IGBT transistors and 7 kilovolts and switching frequency of 7 kilohertz. New concept using IGBT transistor with blocking voltage 1.2 kilovolts and 13 kilohertz switching frequency.
Thank you for your presentation. More questions?
Your solution is designated for trolley buses, yes?
Yes, for trolley buses or trams.
And it's rated for 22 kilowatts, yeah?
Yes, 22 kilowatts, and
My question is, what auxiliary loads need such high power? Is it air conditioning?
yes, maybe air conditioning or this vehicle is input voltage stabilizer using for source for battery charger and maybe air conditioning.
Okay, thank you.
Yes,
Let
please.
me ask you, there was table with prices of transistors and so on. There was the second IGBT, only $7 per each.
Per each.
Very.
This is discrete module. This is discrete transistors, and this IGBT is a big module. Is half bridge on the package. This is,
Later you can tell me where you buy it.
these transistors
Later, okay.
on DigiKey.
For this price, yes.
For this price.
One question? I have perhaps the most important question. You finished the prototype, but how you succeed to sell this concept?
Now this prototype with
So
transistors is finished. This is module, and traction vehicle used module with SIC FAT from Infineon. This is.
Yes, but the question is how you succeed to sell it to any company that they will use your concept.
Okay,
Please.
I have a response. This development is for the Škoda company, and there is a three possible way of the converter. This is one way with discrete H3 IGBTs, and the Škoda company choose the next one solution, and it's now with a confidential.
Okay.
And this solution, it's very similar, but the Škoda company choose the silicon carbide solution.
Okay, this is also not so bad because you obtained money before the study. so thank you. Thank you for So the next paper will be from the area of exchange you. Will be from the area of power systems, electrical machines, synchronous generators, power electronics, and control systems. So very multidisciplinary project, very multidisciplinary presentation. I will be the presenter, Jožef Fritonja from University of Maribor, from Slovenia. So. If I would like to present the topic of the paper in one sentence is how to damp the oscillation of the synchronous generator connected to the grid. So I will speak about the synchronous generators, the conventional synchronous generators which are used in the power plants. These are synchronous generators with the nominal powers from 10 kilowatt until 2000 megawatts. This synchronous generator produce more than 99% of total electrical energy. And these synchronous generators are very non-linear dynamical systems with two inputs, so we need two additional devices for operating. One of the inputs is mechanical torque produced by turbine, water or steam turbine, and the second input is the rotor voltage to generate magnetic field in the synchronous machine, and this rotor voltage is produced by excitation system. So it is funny, but it is true. Even when we have both inputs constant, the variables of synchronous generators are rotating, and where we can see these oscillations. The variables are oscillated. We can see these oscillations in the rotor movement, so rotor speed and rotor angle are oscillated, in stator voltage and in the produced electrical power. So here are the results of the measurements on the real power plant. This is synchronous generator with 30 megavolt ampere nominal power. Here we can see rotor speed and electrical power. So in real condition, we can see that also in this case, by constant inputs, the electrical power oscillates with the amplitude plus minus 10%. So this is this figure once again. so we can see these oscillations better. And here is Fourier analysis of rotor speed. We can see that we have oscillation with the frequency approximately 2.1 Hertz. The most important question is always, is this problem important, or is this only the problem to write the papers or to finish the PhD? The answer is very short. Yes, it is really very important problem. What are the consequences of these oscillations? First, we have increased losses, we have shorter lifetime, we have reduced peak performances, but sometimes it is much more important than because of this oscillation, we have a lot of blackouts of power systems. So here is a list of some blackouts in last years. So what are the reasons that we have these oscillations now? Because we use synchronous generators already 120 years, but we can see these problems in last 20 years. So the main one, there are two reasons. First reason is that we have extremely changed constructions of synchronous generator because of cost optimization. We have smaller damping windings and reduced damping characteristics. And next reason for these oscillations is, for these blackouts, is that we connect many different power systems, and to connect them we need a lot of additional control systems, and these control systems are interacting between themselves and they produce additional oscillations. So which are the solutions for this problem? Yes, we can build the same synchronous generator as 20 years ago, but this is not the most intelligent solution. The better solution is that we will develop a new additional control system which will be able to damp these oscillations. This control system is called power system stabilizer, shorter PSS, because this problem is so important. So we will expect that such power system stabilizers are already on the market. Such stabilizer can be a part of excitation system, either electronic circuit, or model, software model. Yes, we can buy excitation system from many producers which already are equipped with power system stabilizer, but now this almost, or the majority, or I can say all these power system stabilizers are very ineffective. So last year we made an analysis of Slovenian power system. We analyzed the power system stabilizer. Slovenian power system is similar to the Lithuanian power system, and we have 65 generators. Only 36 generators are equipped with power system stabilizer, and only half of this stabilizer is working, is operating. The other half is turned off because they don't increase damping. Either they do nothing or they decrease damping in some situations. So what are the reasons that the installed stabilizer don't operate correctly? First reason is that when we buy excitation system with stabilizer, we have to tune the parameters, and it is very difficult, it is very time consuming, and therefore some operators use factory settings, and these factory settings enable damping for some synchronous generator, but not for all, and not in all operating points. And next reason is that all these commercial power system stabilizers are based on the old linear concept, which is not convenient for such systems, for such a non-linear system as a synchronous generator. So, next question: what the researchers do? Yes, they do a lot of things in this area, so we can find more thousand papers contribution about this on this problem. So I can say all modern control theories were used for power system stabilize their design, everything what is written in control journals. First short conclusion is that the most promising methods for stabilizer are adaptive control and robust methods. It is also very important that in last year we can see a considerable cooperation between three partners: industry, universities, researchers, and operating facilities. And what is for me the most important thing, that I suppose that in the next 5 to 10 years somebody will invent such concept for stabilizing this oscillation, which will be good enough, which will damp enough, and which will be simple enough to be built in almost all new excitation system. So I can say the competition is open. There is no winner here. So until now. This is a short introduction, this is a motivation. I think this is a really important problem, and I will be very glad if somebody of you will be try to find something new on this in this area. So about our paper, so we try to develop a new power system stabilizer. The working in this area in the control system is always the same. First we have to find mathematical model, control plan, then we have to analyze it, then we have to check what is wrong with the conventional power system stabilizer, then we have to survive all advanced control concepts, then we have to develop our new control method, and then certainly simulation experimental results. So about the mathematical model, synchronous generator is connected to the network, synchronous generator, transmission line network. It is is a nonlinear system which is very similar to the mass spring system. The oscillations here are in the area from 0.5 till 2.5 Hertz. The modeling is well known. We use Park transformation. First we obtain 7th order nonlinear model. After then we have to reduce. This model is good for simulation, but is too complicated for control system design and synthesis. Therefore we simplify this model and we obtain simplified linearized model, which is good, is good for description of the dynamic of synchronous generator in the equilibrium point for which this simplified linearized model was developed. So model is simple. We have two inputs, mechanical torque or power, excitation voltage, 3 state space variables, and outputs. The parameters which depends on the operating points are K1 till K6. So if we write this model for nominal operating points, we obtain one set of these parameters, but for all other operating points we obtain other parameters. Here is block diagram. It is third order system, so we have 3 eigenvalues, 2 dominant conjugate complex and 1 trial. Here is the comparison between full order nonlinear model and linearized model. Especially in transient response, we can see that the both models give almost the same results. Here are some results to see the influence of the different inputs on the outputs. So first we change mechanical torque of the synchronous generator for 5% for 10 seconds, and after then we change second input, so this is rotor voltage, for 10% for 10 seconds. Here are the results. Electrical power, the changing in mechanical torque produce these large oscillations. You can see here power, rotor angle, rotor speed, but small influence, small impact to stator voltage. But on the other side, the change in the excitation voltage produce like impact on the stator voltage, but small impact to the mechanical variables and electrical power. So it is very important that this simplified model is used only for the equilibrium state. If we change our loading operating condition, also the parameters of the models are changed. So we can see here, this is one of the parameters, K5. If we change the P, active power, and reactive power of the synchronous generator, the value of parameters is changed significantly from positive to negative value. It is what is new in this paper. New is that it is if we can see this figure, there is no information for us. We can see that the parameters are changed, but we don't know what happened with the dynamics of the synchronous generator. Much better is to investigate what happened with the eigenvalues. So this eigenvalue here depend on the operating point. If synchronous generator is operating its nominal operating point or in some else. So this rectangular is this one here. So we can see if we have the constant reactive power, every curve corresponds to the constant reactive power, and if we change the active power, so from 0 until 120%, so also the eigenvalue here, this eigenvalue moves, and the damping characteristic and oscillations are changed considerably. So we can see we made such researches by more than 100 synchronous generator. Always we can see the same pattern, the same shape, and from this analysis we can find the region. So the borders of the region where are these conjugate complex eigenvalues, which are the most important for the information of our oscillations. We can see that the frequency of oscillation can be changed from approximately 3 till 18 radian per second, so it is for 0.5 till 2.5 hertz, and here is the damping. So the short conclusion is that we can see from this analysis that we have really a lot of oscillation, that we need stabilization system, and that the dynamics of the control plant is changeable significantly in the entire operating range. So what is here we can see the results with the conventional power system stabilizer, which are already used in the nowadays excitation systems. So these are the results when no power system stabilizer is used. So here is active power oscillations, rotor angle, terminal voltage. When we use conventional power system stabilizer and we determine the parameters for this operating point, this is for nominal operating point, and the parameter of stabilizer as determined for this nominal operating point, we obtain very good results. The damping is the oscillations are well damped. But if we use the same stabilizer in some other operating point, in this case we can see that this stabilizer has the damping of this stabilizer is very weakly, almost the same as without stabilizer. So-called self-tuning control. This is one of the adaptive control systems. Here is the block diagram of the proposed control system. So we start with synchronous generator. The basis is the conventional power system stabilizer structure. So we measure one of the variables in which we can see the oscillation, and controller generates additional signal to the excitation system. Addition to this is the conventional. In the conventional power system stabilizer, we use parameters for the controller which are fixed, but we added to this system 3 additional modules. First, plant identification. On the basis of input and output of this control plant, we obtain the structure and parameters of the mathematical model of control plants. On the basis of these parameters, we calculate the parameters for controller, and the decision mechanism here is used to decide what to do. So if decision mechanism see that something is wrong, that the oscillation occurs, the decision mechanism stop the working of this controller. It start the identification. When the identification is finished, then it calculate the parameters, and he change the parameters of the controller of this power system stabilizer. So the modules here are conventional. We can use here conventional recursive least square identification model. We used here state space controller, and so this model are nothing special. So we test different algorithms, and here are some results. here are some simulation results. For these are inputs, load variation. These are changing in loads, and this is a measurement noise by voltage, stator voltage. Without stabilizer, we obtain such rotor speed, so a lot of oscillation. But if we use this self-tuning stabilizer, we obtain in all operating range. So this is for nominal operating point, or this is for some other operating point, almost the same behavior. So rotor speed is changing approximately 10 times smaller as in the case without stabilizer, and this is the output from the stabilizer. So about the experiments, here is we test this algorithm in our laboratory. We used this is synchronous generator, 15 kilovolt amperes large synchronous generator. Instead of turbine, we use 30 kilowatt AC motor with frequency converter, this space and excitation system. And by means of this AC motor, we produce a lot of disturbances. We change the mechanical torque, and here are the results in operating point 5 kilowatt. We can see that the oscillations are always in the during all perturbation very well damped. So far, some conclusions. Oscillation of synchronous generator are harmful and very dangerous problem. Conventional solution is not good enough. We think that adaptive and robust PSS are very perspective concepts. We propose in the paper the usage of the self-tuning controller, which is based on least square identification and LQ regulator. We obtain good results with this controller and simulation and experimental results. And what is the most important, this discussed problem is really up to date, and it is worth to take time and try to find something better in this area. So thank you for your attention. I was a little bit too long. Are there any questions? Yes, please.
So, if I understood correctly, not all the oscillations are dangerous. So can you just briefly explain about those blackouts? What really happened in those cases?
There are two sources for blackouts. There are oscillation in the active power. So if the power from the synchronous generator, the power which is transmitted from synchronous generator to the power system, and other are oscillations in voltages. So the main, it is honestly to say, the main source for the blackouts are the oscillation in voltages. These oscillations are not connected to this one, but these oscillations are also small source for the blackouts. So this is a step beyond, but it is not the most important thing for the blackouts. But it could be also the reason, it could be also source of the blackouts. And there are...
The source for instability.
Yes.
An overall system.
Yes, please.
Yes, at the beginning of your presentation, you showed us results where the frequency of oscillation was approximately 2 Hz.
Yes.
And it was on high power generator,
Yes.
observed on high power. And on your laboratory test stand, the frequency is at the same level, or it shifted?
So I simplified a little bit this problem. So we have 4 types of frequencies. So the main problem by this instability, by this oscillation, are the frequencies that are called the oscillations between synchronous generator and infinite bus. So we have also oscillation between different synchronous generator in the power plant, and the oscillation between some power systems, between areas. So I show only these oscillations. So, and the answer to the question, it is very difficult to say such a general remark if the generator is larger, then the frequency are lower or something. So it depends, especially on the on the connection from the synchronous generator to the power system. How weak is our transmission line? How strong is the transformer between? So in our case, in our laboratory case, we have frequency a little bit higher. So it was 2.1 in the real power plant by 13 megawatt, and by 15 kilowatt we have a little bit less than 3 hertz.
Thank you.
So thank you very much for the questions. So I will continue. So please. Next, our next presenter would like to introduce himself, Mr. Vilnius Gediminas. Do this.
Thank you, Mr. Chairman.
Here is.
So let me first introduce myself. My name is Vilnius Gediminas and I am a PhD student at the Faculty of Electrical Engineering at the University of West Bohemia in Pilsen. Czech Republic. I'm working at the Department of Electromechanics and Power Electronics, and I'm going to talk about one part of my dissertation, which topic is high voltage converter for electrical drives. Sorry. Just now I'm doing research into novel control strategy of single matrix traction converter with variable switching frequency. Now let me give you an overview of what I'm going to talk about. I will start with introduction of AC traction topologies. Then I will like to tell you something about single phase matrix converter and its commutation. After that I will speak about switching frequency of matrix converters. I will show you modular concept, and I will show you measurement on our laboratory model. Finally, at the end of my presentation, I will draw some conclusion. On this slide you can see two ways how the traction drive can be realized. There is classical AC traction vehicle topology with line traction transformer. This transformer is very bulky, and this is big advantage this topology. Next way how the traction drive can be realized is use medium frequency transformer. Using medium frequency transformer dramatically reduce weight of electrical equipment on vehicle on the railways. If we using medium frequency transformer, we have to use a high voltage converter and its filter. For using medium frequency transformer, we need transform low AC traction frequency to higher. European trolley standard are 25 kilovolts per 50 hertz or 15 kilovolts per 16.7 hertz. On this slide you can see modern topology with medium frequency transformer. We use as high voltage converter, we use two matrix converters in serial connection. There are these capacitance create input filter and divide input high voltage. On this slide you can see only two levels of converters, but real application using 14 cells which use 6.5 kilovolt semiconductor elements on 25 kilovolt trolley. These schemes using sorry, never mind. Primary side of medium frequency transformer is using serial connection matrix converter, but secondary side on medium frequency transformer is similar to classic topology. On this slide you can see detail of single phase matrix converter. There is 4 switches. One switch is created from 2 semiconductor elements, 2 IGBT in anti-serial connection. For example, S0 and S1. Input terminals is source and output terminals is medium frequency transformer. They have to attention to forbidden state. There is short circuit of input phases and cut output phases is impossible to use. On the right side on the slide you can see switching combination. There is 4 states. S equal 1 means that source directs connectly to load. States S equals -1 is indirect connection between source and load, and 2 states S plus or minus 0 means that input terminals are disconnected and there is 0 input current. On this slide you can see 2 ways how the matrix converter can be will be commutated in. This is 4-step commutation, both examples. One commutation is using knowledge of input voltage polarity, and this is 4-step switching commutation, and at the bottom of this slide you can see time diagrams when show when the switches are open. Thick lines means open elements with current. A thin line means open element without current. For positive current is the same switch combination as for negative current, but we can show different current with different current. Second way, second commutation is depend on knowledge of output current polarity. There is time diagrams too and switching combination. This is 4-step commutation too. On this slide you can see our combining commutation. There is in section 2 and A there is very small current, as you can see. Therefore we should firstly commutate based on knowledge of voltage polarity. In section 4 and 6 there is low voltage, and we commutate by the knowledge of voltage polarity. In section 1, 3, 7 and 9 we can choose commutation based on knowledge voltage, input voltage, or input or current knowledge polarity. Problem is section 5. In section 5 polarity detection can be hazardous because both current and voltage are very small. On this slide you can see how frequency may affect to weight of transformer. There is marked 2 points. First point means using frequency, low frequency from trolley 16.7 Hz. There is very big weight of transformer iron core. If we use 400 Hz, the dramatically reduce weight of transformer, as you can see on this slide. We try optimization of switching frequency because constantly frequency isn't optimal, because matrix converter have time variable magnitude of voltage. We can adjust actual value of switching frequency according to actual value output voltage to obtain maximal power with minimal switching frequency without saturation magnetic core. The Q means number of switching instances during one period of supply relay frequency. There is balancing input filter capacitors using magnetic core. On this slide is separate levels of drives, and each matrix converter has separate medium frequency transformer. There is no magnetic couple, and we have applied to special control algorithm for balancing input filter. On this slide you can see our measurement model. There is medium frequency transformer, input filter, matrix converter, voltage source active rectifier, and DSP in which our algorithm. On this slide you can see experimental results with using different Q. There you can see if we use odd number of Q and half period of output of voltage in medium frequency transformer starts with their negative polarity of voltage, and half period ends with opposite polarity of voltage. If we use even number of Q, there is negative voltage polarity, and half period ends with negative voltage polarity. This is an interesting result. I will draw some conclusion. Single matrix converter has been presented. Matrix converter commutation was described in detail. Switching frequency of matrix converter was discussed. Control strategy for for designing a traction converter for AC traction vehicles and modular topology was present. That means the new control strategy enabling extensive transformer weight reduction. Some experimental results are shown. Thank you for your attention. Now, if you have any questions.
Thank you, Mr. No questions? Please.
As I understood, you increase the frequency of the voltage by a factor of I don't know, 4, 6, 9, yes?
Frequency or Q? You mean?
I thought Q is a factor.
Q is using for optimization magnetic saturation of transformer. Frequency, switching frequency of medium frequency transformer, not good to use more than 400 Hz because there it creates some adverse states.
So my question is, what is the ratio of transformer weight with your solution?
The weight of the transformer in comparison with classic transformer 10 times change the weight of transformer if we use medium frequency transformer.
Thank you.
So,
Do you do this work with cooperation in?
This work is created in our with our industry partner.
so thank you for the question, for the answers. So our next contribution is in the area of grid-connected inverter. The authors are coming from Technical University of Košice, from Faculty of Electrical Engineering and Informatics. There are two authors, Marek Pastor and Jaroslav Dudrik, and presenter will be Marek Pastor. Please.
Good morning, gentlemen.
Thank you for introduction. The title of my paper is Predictive Control of Grid Connected Multi-Level Inverter with Output LCL Filter. The multi-level inverter isn't so important. It can be any type of inverter. The content of the presentation is some system model, then design of a predictive controller, Kalman observer, explanation why I need the Kalman, then some laboratory setup and measurements result which are not so satisfactory. The control system consists of LCL filter. There is an inverter. It can be any kind of inverter, not just the cascade inverter, and the system is connected to the grid. At first I need some dynamical model. If I want to use MPC control, I need state space model, so I created state space model. I have 6 state variables. The control system is designed in rotating reference frame. It means that I need DQ components, so I need to couple each current in DQ. There are 2 currents in the inverter side, in the grid side, and 2 voltages on a capacitor. There is a table with system parameters. The power is quite low, it's just 1.2 kilovolt amps, just for like laboratory verification. The switching frequency due to the multi-level inverter can be quite low, it's set to 5 kilohertz. There are values of the LCL filter, some resistance of, there are just parasitic resistances, and there are voltages of the cascade 8-bridge inverter. There were 3 8-bridge bridges with voltages of 160 and 30 volts. The idea of MPC control, the MPC controller is usually used for systems with either higher order dynamics or large time delays. The LCL filter is a system of 3rd order, so maybe the using of MPC controller can be beneficial for such a system. It was the motivation, how it will behave. Maybe you are familiar with MPC, I don't know, so I will just briefly explain it. I have some desired value which I want to achieve. Then there is some past inputs, and there is future control moves and the predicted states. The MPC controller chooses the best control move. It's based on some optimization criteria, and it tries to reach this desired value as soon as possible. There is a control horizon and prediction horizon. Prediction horizon is used to compute the future output of a system, and the control horizon is set to consider several control moves in front of, in the future. To design the MPC controller, I need a prediction model. The prediction model is created from a discrete model of a system which was shown on a previous slide. There are several matrices which just need to be calculated. There is nothing special about it, just some math. The cost function needs to be designed. This is a classical MPC control cost function where I have some optimization criteria, J. There is a free system response, Y. Then there are 2 matrices, Q and R, which are used to set up the MPC controller. The Q matrix is used to set the dynamic of MPC controller, and the R matrix is used to limit the dynamics of the output voltage. It means if I have some plant and I don't want to have abrupt changes in the control move, then I can set the matrix R and I can limit those. And if I want to have a precise tracking of my desired value, then I can set the Q matrix and I will optimize the controller in that way. To design the MPC controller, I need to calculate the control vector U on some prediction horizon and P. There are 2 matrices, M and G. Those matrices are calculated according to those equations. Those matrices come from this equation here. Just the first control move is applied on that UK. And to get that first control move, I need another two matrices, Kx and Kr, which are calculated according to this criterion. It's like math. There is nothing special about it because it's a classical MPC controller. Okay, that MPC controller was then applied to that inverter with LCL filter. Here is the structure of the control system. I have an inverter where I measure just the grid current. There are three variables, but I measure just one of them, and it's a grid current. The system is influenced by grid voltage. Then there is the sample and hold, or analog to digital converter. Transformation to alpha and beta. Then to DQ, then I have an MPC controller, but prior to MPC controller, I have a Kalman observer. That Kalman observer is used to extract the complete state of a system, because I measure just one state variables and I have three state variables and the LCL filter, so I needed to use the Kalman observer to measure the, or to predict the remaining system states. The MPC controller, this block here has quite simple structure because there are just like two gains or two matrices and they are added together. There is some delay and then I get two voltages, UD and UQ, and those voltages are then transferred into alpha beta, and just the beta voltage is used for the inverter because it's only one phase system. Okay, that Kalman observer, I think you are familiar with Kalman observer. I have some dynamical process and then I have Kalman observer. That Kalman observer can do like two things. In this case, it can improve the information from a sensor because there is always some noise. So I can remove that noise from a sensor by using the sensor equations, and then I can predict or observe the system state if I'm missing some of the system variables. It was my case. I had only one measured system variable, and the remaining two, it means like inverter side current and capacitor voltage, were observed by Kalman observer. I had some laboratory setup. It's quite small system, so also the laboratory setup is quite small. There is RT lab to control the system. There is a cascade inverter, there is a grid and some measurements. Here you can see the parameters of the MPC controller. There is a mistake, I'm sorry. Which were used in this laboratory setup. The sampling period of a system was 200 microseconds. It was limited by the speed of my computer, which is quite old. So that's, the system is sampled at 200 microseconds. The prediction horizon of the MPC controller was set to 10. The control horizon was set to 3. And you can see the values of matrices used for MPC controller and for Kalman observer. Okay, there are some measurement results, and it's like always, that's the biggest problem because you can see like two things here. The first one, the system or the LCL filter is undamped. It's a like third order system which can oscillate, and there is no active or passive damping added to that system. Just the MPC controller used to damp the system, and you can see that there are two currents. It's ID current and IQ current. There is a reference, the dashed line, and the measured, and also the reference, dashed line, and those not nice measured results. So you can see that the system is stabilized because there are no oscillations. If I set some value of the current, then the system is stable. But the problem is that the system or the MPC controller needs the exact model of the system. And my model is consists of two things. The first thing is the physical model LCL filter. I know the exact parameters of those inductances and the capacitor value, but what influences the system is also the grid. And the grid has some inductance, which is in series with this LG inductance of the LCL filter. But that inductance was unknown for me, so the result of not considering the grid as a part of a system was that if I set some value of a current, then the controller isn't able to reach that value because the model of the grid is missing. So it's like the motivation for the next work. is to identify the grid inductance. The system is quite stable and it's operating in that small scale in the laboratory, but the main problem is that I didn't identify the inductance of a grid and it influences the model. So it's like the conclusion of my presentation. So thank you for your attention.
Thank you for your presentation. Please, questions?
Is it common for dumping the noise or removing the noise? Doesn't always work. So how efficient was in your situation?
Well, I needed to tune those two matrices because one matrix can be calculated quite exactly because I can measure the noise from a sensor, but the other matrix can be like just the try and error. So it was like quite good, but the main problem is that grid inductance. It's not known, and also it influences the Kalman filter because that Kalman filter uses the model of a system, and it also influences the MPC controller. So it's like two parts of a control system which are influenced by one unknown variable.
Yeah, to tune it.
Yeah.
Yes. Thank you.
And thank you for the answers. So our last presenter is coming from University of Ostrava. He's Mr. Václav Kolar. The title of the paper is Distributed Measurement System with GPS Synchronization and its use in electric traction. There are three authors, Roman Hrbat, Václav Kolar and Tomas Mlcak.
Thank you for introducing me. Let me present our paper. Our collective deals with measurement in power electric engineering, and usually measurement is distributed. That means we measure in several places which are distant each from other kilometer or several kilometers. This is one example. Another example, distances are also again kilometer or more. So we need to have some system which is able measure in different places simultaneously. For measurement we use this simple data recorders, computer, usually a laptop computer, and analog to digital converter. This is analog to digital converter by National Instruments, and it is equipped with simple voltage dividers and some overvoltage protection and low pass filters. And this is measuring software created in LabVIEW system. It's nothing special. But for distributed measurement, we need some time synchronization of this measurement. Because time accuracy of computer internal clock is not sufficient for our purposes. And for example, online data transfer, we reject it because it's not possible when measurements are several kilometers each from other. Sometimes it is in forest somewhere far from civilization. We experimented with radio time synchronization, but it was problematic. So at the end we decided to use GPS synchronization. Accuracy of GPS signal is very good, better than 1 microsecond, much more better than 1 microsecond. For our purposes we need accuracy about 100 microseconds. So we developed GPS time synchronizers, and we use one additional channel in our measurement system, and this channel measures timestamps from this GPS synchronizer. This is
simplified diagram and photo of synchronizer. When we finish measurements, we have several data files, each from one measuring place, and in this software we put the data together. This green line is signal from GPS synchronizer. This is signal from another GPS synchronizer, and so on. And this software puts data together, and these pulses are used as a trigger for joining data together. But there is also a problem, because internal clock of analog to digital converter is not perfect. There are some small fluctuations in frequency, so sample rate of analog to digital converter is not always the same. The error is small, maybe 5 milliseconds per hour, maybe 10 or 20 milliseconds per hour, but sometimes we need to correct even this small error. The best solution of this problem is to use oscillator in analog to digital converter, which is tuned by GPS signal. This is possible, but very, very complicated. So we decided to use software solution. When here we have measured data, we do software resampling of this data. So, and this software does also this resampling. So at the end we have one big data file from many measurement places as if it would be measured in one place in one computer. Here is one small example of measurement and measurement results. We measured in traction transformer substation which supplies railway traction 25 kilovolts, 50 hertz. We measured voltage and current here. We also measured voltage and current here on 1010 kilovolts, but now it's not important. And we measured also voltages in track relay substation. Track relay is a significant part of track circuit. Track circuit is circuit which checks if some segment of track is free or segment of track is occupied by train. These track relays worked with frequency 275 Hz. Distance between this transformer substation and track relay substation was about 1 kilometer. And here you can see example of results, and we can see that sometimes there is some interference between track current. This is traction current. This is 50 Hz current in traction line, and this blue voltage is voltage on primary coil of track relay, or opposite, sorry. This black is square voltage 275 Hz on primary coil of track relay, and blue one is voltage of second coil of track relay. And sometimes amplitude of second voltage is lower or higher, and thanks to our synchronized measurement system, we found that this is because of interference between these peaks in track current and edge of this square voltage. This phenomenon isn't dangerous for train operations, but there is such phenomenon. It's here only as example of usage of our system. I tried to also make some simulation of this phenomenon, and simulation results of simulation are similar to our measurement results. So that's all. Thank you for your attention. Sorry for my English.
Thank you for your presentation.
Questions?
Fortunately, there are no questions. So we can finish our session just in time. So it's 10. And thank you for your attention, for your questions, and for your presentation. Thank you.
gentlemen, welcome to this session, which is last session of Electronics 2015 in Palanga. This session is mainly in the area of electronics. We will have presentation and research work in the area of grid and smart metering, sensor-based body temperature control, power optimization or energy optimization, and PWM pulse width modulation. I'm glad to announce that all presenters are here in this session, so hopefully it will be a really productive session. I just want to ask the presenter, please follow the 15 minutes presentation, including the discussion as well. The first presenter is from Czech Republic, Wojtek Planik. That was my best pronunciation, and the title of presentation is Control of Grid Connected Modular Multi-Level Converter. Please.
Okay, Mr. Chairman, thank you for introducing me. Good morning, gentlemen. My name is Wojtek Blaník and I'm from University of West Bohemia, and I currently work at the Regional Innovation Center of Electrical Engineering. And this presentation is about modular multi-level converter. This is my presentation outlines. Few words about multi-level converter based on cascade 8-bridge topology. After that, a few words about the control, and the final, the simulation and experimental results. The main objective of our research was to design an AC/DC converter, which is fed directly from the 6 kV AC grid. It doesn't mean without the bulky transformer, and the final power of converter was designed for 6 megawatts. Our proposed topology is based on cascade H-bridge converter, and there is a 3 H-bridge converter per one phase. Okay? 1, 2, 3. And the main attention of the control is concerned to the voltage balancing of the voltage on the output of each cell, and this voltage balancing is solved separately at the control structure level. Our designed control use 3 separate control lobes. It doesn't mean the first control lobes or the first phase and the same control lobes for the B phase and C phase. And in this, it's the same for each phase, and the control is composed of the mathematical model, voltage control lobe, where is used P control, and current control lobe, where is direct current control, which provides by proportional resonant controller, and also the path for the balancing of the voltage. The modulation in this case is PS, PWM, and it's realized in FPGA. And now in detail, the control structure for the converter. It's for the single phase part of the converter. The mathematical model is based on the mathematical description of the multi-level converter, and the output modulation signal is there. The voltage in this case is the control, the sum of the voltage of this 3 cell to required value, and there is use a classic PI controller, and the output value is magnitude for the requirement current. It doesn't mean there is a computed requirement current. This is the green one, and it's compared with the actual current of the converter, and error is the input signal for the proportional resonant converter, which provides the direct current control. The output signal is summed with the mathematical feed-forward term, and the output, the final output signal, is the modulation signal for the first cell of this converter. The second and third modulation signal is computed, and it's there's a this signal can be different. It's depend on the voltage on this voltage on the output voltage of this cell. In this case, we have the first cell as a master mode, and the second it's in the slave, and there is in the slave too. Does it mean we use a difference between the output voltage of the first and second cell? It's an input for the PI controller, and this output modify the value of the modulation signal for the second cell. And the same way is used for the that modulation signal. There is use a difference between the voltage of the first cell and the last cell. And the modulation technique in this case is a phase shifted PWM modulation technique, which provide the voltage at the converter AC side will be in this case 7 level, and it's a standard modulation technique for multi-level converter, where is the 3 source signals with fixed phase shift, and the modulation signal. In this case, we use a 3 modulation signal. It doesn't mean the first for the first cell, second for the second cell, and so on. And now some simulation results. There is used some equivalence current source as a load, because we need tested converter behavior under non-symmetrical load. It's the first behavior where the converter under symmetrical load with 9.45 kilowatts. There is a 3-phase voltage and the 3-phase currents, which are in the phase against voltage. This is converter behavior for the step change of the symmetrical load, but interesting it's these figures where is the converter under non-symmetrical load, and the balancing voltage does it mean the voltage are controlled to the requirement value, and in this case it's during 1 second. And for the non-symmetrical load also are the different value of the currents in each phase, and also the current ripple is different. It's caused by different modulation signal for each cell. And now some experimental results. In this case, we use for each cell separate controlled inverter, which provides some changing the load for each cell. Yeah. The final test was for the reducing power just for the 1.1 kilowatts, and the control was implemented in DSP Texas Instruments 335, and PSWM was realized in FPGA modulator Altera. This is the behavior where is the converter under startup sequence. The converter current was limited by the proper function of the proportional resonant controller. There is the final voltage of the AC on the AC side of the converter is the 7 level, and after them the currents ripple are lower, yeah, and the current is also in the phase against the source voltage. And now the last experiments, the converter are under non-symmetrical load. In this case, the second cell of the converter is loaded just 90% against the first and third cell. And during 1 second, it's stabilized the voltage to requirement value. Okay. This control provides voltage balancing on the individual power cells. What is important on the directly to the control structure level. There is not necessary use some change in the FPGA modulator, and it's the very simple and powerful approach. It can be used implement, and we use just the conventional proportional resonant and proportional integral controller. Thank you for your attention, and your question are invited.
Any questions? Nothing? Alright, thank you very much. Thanks again. Title of second presentation is Deeper Layer Body Tissue Temperature Control Using Multisensory Transducer. Let me help you with this.
Thank you. Measurement of deeper layer body tissue temperature is very important for many purposes. For sportsmen, for people who works in extremely environment. It is known some methods for measurement of body temperature. This method can be divided in two classes. It is non-invasive method and invasive method. But invasive method, which is used now, is can be used only in clinical environment. And for this purpose, it's very important to have device and method to measure temperature of body tissue with non-invasive methods. For monitoring of deeper layer human tissue temperature, when tissue is cooling or heating. Our idea was to form a design of transducer in which we can form two channels for head flow. We hypothesized that these two flow can be equivalent, and it's very important to cover these channels from environment, because environment, as show our praxis, have very important influence in result of measurement. On ground of this design, we can do equivalent resistance circuit of these two head flow channels. What is shown in this fig 2, and from this equivalent circuit we can show equation for first channel and for second channel, and if we hypothesize that both flow are equivalent, can do equivalent, and this condition, we can derive equation for calculation temperature in deep layers of tissue. But for experiment, we can do digital experiment and physical experiment. For the digital experiment, let's use a penny equation, and value for modeling. Let's use this, which is used for modeling in many times, in many articles are published. Because in construction there's used thermistors, and for linearization of thermistors characteristics, there's used well-known Steinhart equation, is this 6 equation, and for experimental transducer, these thermistors were used from company Can-Term, and after calibration and calculation coefficients, 3 coefficients for thermistors, we have accuracy for transistor 0.02 degree Celsius. Results of modeling distribution of the temperature fields in tissue and under temperature transducers when environment temperature is plus 15 grad Celsius. Why 15 grad Celsius? Usually this temperature is used when physiological experiment are conducted. It is important to select ratio of resistance for model, and this conduct modeling, numerical modeling, temperature and ratio, and what you see from ratio 4 change is minimal. According to the results of numerical simulation under ambient temperature 20 degree and under transducer, it is skin surface with 30.0. Value of measurement temperature on the physical model using experimental transducer with 30 plus minus 0.28 degree. And second experiment was for environment temperature 15 Celsius. And we have some results of measurement. Using these results of measurement, we can calculate the temperature in deep layers of muscle. This is made numerical experimental experiment for approximation using different order of polymer, and for 6th order polymer we have this result, and for a higher order of polymers it haven't more exactly results. For calculation of deep layers temperature, we have equation, and according to this equation, we calculated temperature in deep of 3 centimeters in respect of skin surface. Why 3 centimeter? 3 centimeter usually use it all many of researchers in the world, and needle probe, which use it for direct measurement of temperature in deeper layers, usually is about 3 centimeters long. According to our results, muscular temperature depth of 3 centimeters measured using proposed methods and transducers and techniques was 32.45 plus minus 0.6 degree, and this value measured using needle thermometer was this one. That is different, not big, but using needle is no one want to insert 3 centimeters under surface. And this is not fine and it's danger. And conclusions. The use of the proposed design of temperature conductors contains 4 precision thermistors. It's a novel, non-invasive way to determine temperature of deep layers of tissue. It's known some sensors with 2 thermistors and zero flow method and another. As I say, to ensure the body tissue measurement accuracy, 3 transducer must be covered using a cap with good thermal isolation that minimizes the influence of ambient temperature. We used polyurethane foam type Thermoflex. That is in practice the better thermoisolation material. Transducer was attached to the body using elastic band and can be immersed in cold water because physiological and experiment they use immersing leg in cold water and for 15 or 30 minutes. It is not fine, but this time we can control without using needle thermometer. Thank you for your attention. I'm sorry for my bad English.
Any questions you want to ask?
It was very interesting, but probably we can говорить и по-русски.
О, да.
Можем поэтому
А,
поговорить,
хорошо,
потому что я
пожалуйста.
совсем принципа не понял это.
Ага.
Хорошо. Sorry, that I said
Да.
I couldn't understand the principle of operation.
Да.
But
Окей.
This is very good.
Yeah. In comparison to this other sensor, how fast does it settle to this value when you attach it, when you apply it? How fast do you get a stable result?
If you put person underwater, leg or arm, only leg or arm, you must like 15 minutes or 30 minutes.
Okay, but above the water? I mean, in regular application?
No, it is this problem that changing of muscular deeper layer temperature is very slow and down and
Yeah, this equation.
it is some data that under very high load of man temperature of body might be high 41 degree Celsius. This is very high.
Yeah.
If more, it is death. But it is experimental data from soldiers, which go in march with all ammunition.
Right. Thank you.
Thank you very much. And next presenter is from Czech Republic, Petr Milinek, and title of presentation is Heterogeneous Network for Smart Metering, Power Line and Radio Communication.
Okay, thank you for introducing. My name is Petr Minek and I'm from Vilnius University of Technology from Czech Republic, and I would like to say a few words about the heterogeneous network for smart metering issue. The outline of the presentation is the following. I say a few words about power line communication, then about simulation of radio wireless network, and finally about heterogeneous network and the proposed hybrid power line wireless module. The motivation of this work was to answer on this question, primarily of the first and second one. What is the primary motivation for deploying of a wireless power line network, and which power line communication standard will be deployed for the future smart metering issue? There is no doubt that the future smart grid will exploit multiple types of communication technologies. In this figure we can see the example of the smart grid network, and if we divided the network on the transport and access part, we can say that for the access part there are the commonly most widespread technologies are radio and power line communication. The power line communication can be divided according to the frequency band into broadband and narrow band. The broadband achieve high data rates, but there are problems with noise, communication range, repeaters and so on. Therefore they are directly focused on home area networking, internet access, building automatization and so on. On the other hand, the narrowband power line communication achieves a high communication range but with small data rates. Therefore they are used for smart metering and remote data acquisition. The big advantage of power line communication like wireless that they doesn't need new wire, but there are also many disadvantages like power line characteristics, especially noise. In our work we propose the experimental radio network, which contains short circuit current indicators on power line poles, and we want to simulate in the radio mobile software the signal coverage, attenuation and path losses. In this figure we can see the example of the signal coverage without repeater from one measuring point to data center, and they are not in direct line of visibility. Because there are obstacles in the form of the mountains, as we can see in this figure, therefore we simulate the signal coverage with a repeater, and we propose some repeater height. And when we want to achieve the at minimum reserve of 6 decibel, the antenna height must be located at the minimum of 15 meters. Therefore, the single radio technology for smart metering or smart grid issue, in our opinion, is problem, because there are necessity of repeaters, there are obstacles in the form of mountains, building, forests and so on, and also there are big influence of the weather. Therefore we propose the heterogeneous hybrid network for coverage large or rural remote areas, which consist of power line communication and wireless. After that we want to find which power line technology fits best for smart metering issue. I can say that the narrowband power line has several advantages in comparison with broadband power line. Because the broadband power line solutions are not directly designed for smart grid issue, they are designed for home area networking and so on. But high data rate narrowband power line standards directly target on smart grid requirements. After that we analyze low data rate and high data rate narrowband power line standards, and it is possible to say that low data rate standards can be considered as frozen, but on the other hand the high data rate narrowband power line standard are today still being deploying. From the application point of view, we must take into consideration two contrary requirements: robustness and long-range communication against high-speed data rates. Therefore, we carry out some experimental measurement with this type of power line communication modem with different topology size and so on. We measured loss rate and data rate for different standards, modulation and modem type. According to this result, we choose the solution from Maxim and this type of modem. And we develop the hybrid powerline wireless module based on G3 standard and chips from Maxim, and also with wireless solution based on XB Pro 868. This module can be used for hybrid heterogeneous network, but also for some redundant path or redundant channel. After that, we carry out some measurement only for the powerline communication part in this condition. And in this figure and in this table, we can say the data rate for different type of modulation or modes. And I would like to finish with some conclusion. We propose or introduce two possible communication techniques for smart metering and smart grid issue, the radio and power line. They are also different, but for example, high-speed internet everywhere, for example, in every electrometer, I think it's not impossible. Nowadays, it's commonly used for remote data acquisition for electrometers, especially mobile network, but there are also disadvantages in price, response, and so on. Therefore, we propose the hybrid power line and radio module, which can be used, for example, in street light control and so on. And the communication will be the key aspect of the future smart grid and smart metering deployment. Thank you for listening. I'm open for some questions.
Audience, any questions?
I have questions. That's very interesting. And however, just if you use wireless, you use radio. It's not power line. Power line communication is usually directed power line. It's only for the button. It's not important things. But if I'm not wrong, you install antennas in some cases on the tower and then send the information. No using line, just using radio. There's nothing to do with power line. That doesn't matter. However, you in this way, in your way, you have to overcome some obstacles like this. We have some similar problem in using a power line. Probably we could use a wireless application, since when you have joined all the cable inside, and the cable is very long, about 1.5 kilometers. Therefore, attenuation is very hard. Therefore, that's the problem, how to couple it. We use inductive couplers, and then attenuation is very high. Perhaps it would be your idea, it would be okay if we use a modem, special modem on one side and another side, we could send the information they're using wireless. That's a very good idea.
Yeah. But the narrowband standard can achieve the distance of kilometers.
Yeah, but we use BPL.
BPL, yeah, BPL is only for short range.
That's right. That's a very good idea.
I would like to ask a question. You outlined disadvantages of both of these technologies, but I finally didn't get what you proposed. Either you propose to use all these two networks in parallel, and then some intelligent node defines which channel data are managed to arrive, or you propose to run on certain segments wireless, on other segments power line communication. Which is your proposal in this situation?
Yeah. We receive the measuring point of the short circuit current indicators on the pole. They are real installed. And therefore, we want to find a solution, different solution, to communicate from this point to the data center. Therefore, we realize some simulation is possible, and the wireless, only the single technology like wireless, it is not possible to use. Therefore, we propose to combine and for example, for remote data acquisition for electrometer, the first part, the access part of the path, is mostly used power line communication. After that, they use different technologies. Therefore, we think that it will be better to combine technology, not use only one single. But always it depends for the area.
You got your answer. All right. Any?
You have used XB, but this technology, is it capable of intermediate modes? That is not direct line of sight communication, but communication through intermediate modes?
We
try to realize the communication without repeaters, because this is expensive to install and find the location. But if they are possible to install and locate some repeaters, that is no problem to communicate.
So there were no communication nodes in the line between the transmitter and
No.
receiver?
All right. If you have further question, you can catch up with presenter after the presentation, after this session. So next presenter is from Estonia, Tasif Ahmed. Will be presenting power optimization in heterogeneous cognitive radio network.
Thank you for introducing me. Power optimization in a non-coordinated second infrastructure in a heterogeneous cognitive radio network. Hello everyone, my name is Tosif Ahmed, and as he already mentioned, I'm from Tallinn Technical University. I'm doing PhD in Department of Electronics Engineering. This is my basically topic of research, and let's see what we have in our presentation. Some key points which I will be giving a brief overview would be an introduction about cognitive radios, then my system model, which is basically based on a decentralized network architecture, and how the cell is basically operating, and simulation, some results, and in the end conclusion. Basically, why we need cognitive radios. Cognitive radios were put into the picture because the assigned So the spectrum which we have to use for the communication, a usable spectrum, has already been assigned. According to one survey report which I have studied some time ago, there is almost 85% in US spectrum go underutilized. The spectrum is already assigned, let's say, to TV channels, but the 85% of the time it's being underutilized, so it's available. So researchers have proposed this kind of a radio that called cognitive radio, that is basically smart context sensitive radio that can be programmed and configured dynamically. So if you must have, many of you have seen movie Transformers, so it's basically a radio transformer which basically adjusts itself according to the radio conditions and environment. So cognitive radio is basically the kind of system which enables this kind of a dynamic spectrum access from another resources, like the people who have paid for this spectrum. Cognitive radios basically work in a cycle that is called cognition cycle: spectrum sensing, spectrum mobility, spectrum decision, spectrum sharing, and environment. So here is the part which I am actually researching on spectrum decisions and sharing. So this is the thing which I am mostly focusing my research on. For example, this is a decentralized network. Basically, I am considering myself only to the 3 cells, 1 cell, 2 cell, and 3 cells. And this is basically secondary base station. This is not the like a permanent setup. So it's like an ad hoc network. So decentralized network architecture means that they don't have a backbone network which carries their information between the base stations. So this architecture is basically every cell is independent from each another. So in this cognitive radio architecture, these cells can be owned by different vendors. I'm sorry. What is basically my contribution in the research community? For example, this is one radio base station, and this is my area of interest, and how basically decentralized architecture works. Every base station hosts some kind of algorithms or software which do this kind of a spectrum sharing and decision making tasks. So here, this is the component which is very key in my research. It's based on the RLDSA. DSA is the dynamic spectrum access methodologies, and RL is the reinforcement learning technique. So this technique has been previously used, and I'm reusing it in my research to further enhance the vision. For example, this whole architecture, or this part, is basically called the RL DSA controller. it's basically sensing the environment. Could be measurements based on the user's choice. Could be SINR, signal to noise and interference ratio, spectral efficiency, and another thing. So here there is another feature involved, which could be an optional feedback from the environment. So based on the environment, this or a reinforcement learning based algorithm, it sees that now which channels are available, so we have to move our users to that channel. So basically this is the key component here. So how basically cell is operating? Each cell is trying to achieve the best possible spectrum allocation, and there is one you can say like a constraint that all these cells will not try to assign spectrum. So they have a kind of relationship. When one cell is doing the spectrum management, the another cell is doing the operation. So it's not doing the offline management. So basically, resources are basically assigned on the medium term basis. So after a few minutes, it's not like every other second there is this algorithm, because this algorithm is costly and it creates overhead in the communication. So that's why it's taking some time. Then how this procedure works, basically the reinforcement learning algorithms, they start from a random combination of the available frequency channels, and then they assume that which one of is better based on this kind of interactive measurements from the environment. They see that which channel is better to for the assignment. And basically this is my contribution towards this, that how previously people have used frequency optimization but not the power they were using the constant power. So here I propose the concept that power should be optimized. Let's say the people are the user who are at the edge of the cell. They need more power as compared to the people who are closer to the cell, closer to the base station. So there should be a balance between the power. Someone should have higher power, someone should have lower power. So this is the basically objective function or the optimization function, which during the iterative process we need to maximize in order to achieve the higher power for the resources for the transmitter, but depending upon the constraints that it should not generate any interference to the neighboring cells who are using the same frequency bands. So some of these constraint on the power allocation algorithm, that power cannot go more than the available power in the cell, and the second constraint is that the power assigned to any transmitter should be less than a threshold. The threshold can be assigned by the user, or it can be set by the environment, that whatever the interference is being received from the other cells, that should be below this limit. And if this frequency carrier, the chunk is not being used, so the transmitter, it means that frequency channel can have that power. So this condition would be null and void, and only this condition would be effective. So basically I have considered two simulation scenarios. One, as it was done in previous research, that with the constant power transmission power, and then comparing these results with my power optimization algorithm. So based on this, I will show the results. What are the results? Basically some simulation parameters that the users are basically scattered randomly in the cell, but they are not moving. They are like fixed during the simulation time, and the number of the users, they are also constant. Cell load, it means cell load is not changing, and all the users are trying to capture the maximum band. So I'm considering the full load buffer model. So it means all the users are trying to capture as much resources as possible. So it's like a worst case scenario for the to analyze. Some other parameters. I would not go into the details, but if somebody is interested, that what was the thing. So some results, basically I would define the spectral efficiency. These are the three parameters on which I am measuring the results and comparing my results with each other. Spectral efficiency is basically the amount of successfully delivered bits per unit of time per spectrum. And then the second component is basically the user's satisfaction, the user happiness. But it's, of course, we don't go and ask user that are you happy with the services. It's based on the measurements from the environment that the quality of service which user is being received, is it okay? So it's the percentage of amount of time when the user throughput is below the target throughput is called dissatisfaction probability. And one very common and very well-known signal to noise and interference ratio. Sorry. So here are the figures. This is the figure with the constant powers, and this is the optimized power result with the little gray color. So here it's not so big, but there is a very small difference, is a big difference in the communication system. So here I'm achieving a 4% efficiency, 4% gain in the spectral efficiency. If you compare the system, both system in the signal to noise and interference ratios, then it's some parts I'm getting up to 10 dB gain, and the lowest gain where I receive is around 0 dB. So overall the system is performing better. The power optimization has not degraded the system, although it's a very complex and heavy algorithm. It takes time, but it has not degraded the overall performance of the system. And dissatisfaction probability here, it's not much difference. It's more or less the same. So what is the basically the moral of this story here? That if we compare this place, it means spectral efficiency, which is the throughput of the system. So it means that there is a throughput available as compared to the same satisfaction level of the users. We have more resources we have in the same resources more bandwidth available for. So it means the capacity of the overall system can be increased. Maybe 5-10 users can be put more in the cell. So this is you can say one positive aspect. Conclusion and some future work. Basically, novelty of this work is on the reinforcement learning based spectrum assignment technique and based on power optimization. But this is basically a suboptimal approach. Why? Because reinforcement learning is one separate algorithm, power optimization and separate algorithm. So you cannot run both these at parallel time. So one will iterate, another will compute on based on that value. But still, it's giving us better performance as we have seen in previous slide. Some future work would be some dynamic environment where there could be more macro cells, femtocell combination could be computed. Mostly people don't consider handovers, and I think I'm planning to do some simulation based on the handovers, that how the algorithm will behave when there are handovers. And finally, there is a key thing where people are like trying to it's like a new phase, new area, cognitive wireless sensor network. I am planning to apply these power optimization and frequency optimization algorithms to the sensor network techniques, sensor network. So that's basically my research. Thank you for your attention and time. If you have any questions.
We have 2 more presentations, but if there is a question, please very short. No, thank you.
Yeah, thank you very much.
All right, I will be presenting the next paper, Novel Smart Eco Model for Energy Consumption Optimization. This is the Internet of Things approach, actually. And this research is joint collaboration between Department of Electrical, Electronic and Computer Engineering, University of Pretoria, and University in St. Paul the Apostle in Republic of Macedonia. The outline of my presentation is introduction, energy management process, overview of advanced techniques for data analysis, and our proposal, and we conclude the presentation at the end. For introduction to what is the motivation of doing this research, we can see that we have a growing in global population, and there is a statistic that is saying that we have almost 80% of carbon emission in the cities, and cities also represent 3/4 of energy consumption. So what we are looking for, we're looking for a sustainable environment. So our goal is to reduce carbon emission, and also the best thing for us is also to reduce energy consumption. So what is the approach? One approach can be like moving to smart cities. So smart cities in terms of managing the cities, in terms of improving quality of life, and also reduce this carbon emission, which help us in sustainable development of sustainable environment. For sustainable energy management and smart cities, of course, we must have standards and architecture available. So how we can have smart cities now? One way is we start to have smart homes. To have smart homes, one way is to start having sensors, for every appliances that using the energy. We consider a sensor and we interconnect all the sensors together, and we try to measure the energy. And of course, there are some external parameters like weather or user behavior pattern which may affect the power consumption. Energy management process. First, we define energy management, a process of control, monitoring, and conserving energy consumption in a building, which lead to save the power consumption, save energy, and also reduce negative impact on environment. This process, as you can see, we have 4 steps. The first one is measuring energy consumption. I will explain how, and collecting data. And in the second stage, we try to make a data analysis to find out possibility to save energy. And in the third step, we try to analyze collected data to see if there is any improvement in energy. And we can also repeat this algorithm for improvement. For the first phase, which is measurement of the energy consumption, we can use smart devices like interval metering system, which automatically measure energy consumption in regular time intervals. And the output of data can be in time step and also the value which is measured. But also we can use some of the recently published data set like Blue D, Red D, and Green D, which was published in 2014. But the fact is, for this data set, they are for very short period of time, less than 1 year. And they didn't consider energy consumption for every appliances, and not also various power measurement unit. We have some other options like using data echo data set, UKDEL, and AMP data set, which we go through the details and characteristics of each of these data sets. The first one, echo data set, is for 5 households in Switzerland, and the period of energy consumption was for almost 8 months, which is less than 1 year. And they consider measurement like for voltage, currents, and phase shift between voltage and current. The second data set is UKDEL, which the duration of energy consumption is 499 days, and they consider reactive and real power recording for 4 household appliances. And the last one is AMP dataset, which is for 2 years, and the interval of energy consumption is every 60 seconds. And they don't only consider energy power consumption, but also gas and water consumption. In our approach, we try to use this AMPDS and go through the analysis. This is a basic analysis. We try to analyze the energy consumption based on what? For 10 most commonly used appliances like dishwasher, oven, hot water, and heat pump. Based on this analysis, we see that this hot water has, and also heat pump, has the highest energy consumption based on the monthly data. And if we go to the next slide, this is the data aggregation for per hour. We can see that heat pump between time 14 to 15 hours has a peak of energy consumption. So this is probably, for this case study, this can be probably, the reason can be correlated to the outside temperature. And to mention that, to correlate between energy consumption and the air temperature, we define a new concept, which is degree days, and we include historical weather data. That also data is available on degreedays.net. In that degreedays.net, we have also two parameters, HDD and CDD. The fact is, this is the AMP data set was actually captured in Vancouver area. So for HDD, and that the conclusion that we got from the analysis, which is regarding the heat pump, we can conclude the outside temperature is probably is cold. And so therefore we consider these HDD parameters, which show us how much in degree and how long in days outside temperature is below the base temperature. And we consider the base temperature 19.5 degrees. In the software we can change this temperature and find out also the analysis, more analysis. For the more analysis we use regression analysis for 2 periods of year, one between April 2012 and April 2013, and April 2013 and April 2014 to find out correlation change in energy saving. In this two diagram, what we can see, this line is actually that regression line, and R square representing coefficient of determination, which can tell us how good the correlation is between energy use and degree days. So if this R square is near to 1, is the ideal situation, power consumption is good, everything is good. But if it's less than 0.8 or 0.75, we need some improvement. In this case, in this case study, the heat power, as you can see, is less than 0.7 or 0.8. This heat power is acting poor, and we need some improvement to like house insulation, and or maybe adding new device in the system that we have, or maybe change the user behavior of the system. Based on the advanced techniques, we can see we need some, based on this analysis, we see we need some advanced techniques for data analysis and also prediction. For data analysis, we can use non-intrusive load monitoring, or the other one is discrete probability and signal measurement. And for prediction, we can also use data mining, classification, and clustering. Very short, we choose artificial bees colony algorithm for our proposal. So this is the algorithm, and what we can do based on that ABC algorithm, artificial bees colony algorithm, we try to have obtain a periodic list of appliances with the current voltage. So what we can do now, we try to modify ABC algorithm, and we add some external parameters like weather or user behavior patterns. And now we have a new concept, addition average, which three parameters, depends on three parameters, time, standard average, and predefined usage. Each of them, for example, time stamp can tell us checking if usage time of a particular appliance is longer than usage time for that appliance. A standard average can tell us what is normal usage on average for that particular time of the year. And the last one is telling, for example, the user can configure at the beginning of the implementation, they can configure the preference for that system. This is the proposed algorithm, Smart Eco. We try to classify all appliances that we have in one house into low, medium, and high priority. If the appliance is in the low and medium, we try to measure the energy consumption and also consider the external values. And we can, after that, send some feedback to the user. For example, in this one example is here, figure out that your heater can be turned off for the next 10 minutes to optimize your electricity usage. Do you want or not? This is one application that we can use. And the hardware that we have in this in our system consists of sensors for all appliances. Okay, so they measure energy consumption. They send the data to one internal hub. It can be like wireless hub, and this hub will run the algorithm, run this modified algorithm, and give feedback to the user. As conclusion, we try to propose a complete energy management process. Consists of collection of energy consumption data and analysis. And based on the result, actually this is very, we are trying to implement something in the Republic of Macedonia. For the future work, we need some experimental result to conclude this research work. Okay, if there is any question. Last presenter. From Czech Republic, right?
Does it work? Okay. One. Okay. Hello, my name is Jan Jeřábek. I'm from Czech Republic, and first of all, let me ask the organizers of this beautiful conference to consider my following proposal. You know, I'm the last presenter of this conference, so it would be nice tradition to give the last person the right to start the next conference in next year. The conference will continue during the year, but of course this is only a joke. Our research is focused on active elements that are or that possess electronic control of gain, intrinsic resistance or transconductance. This is useful for generators, tunable filters and oscillators, and of course there are many active elements already reported in literature. One of them is Z-copy controlled gain voltage differencing current conveyor. It's a very long name, but the basic is really simple. It consists of two active elements. One of them is operational transconductance amplifier with controllable transconductance, and second is electronically controllable current conveyor of second generation that has controllable intrinsic resistance and current gain as is described by these equations. We proposed this CMOS structure. Actually it consists of three sections. First is OTA, then CCII, and then current amplifier section that makes the gain section. We found the application of this active element in many areas. One of them is a functional generator. This one is without duty cycle control. The structure is really simple. It contains or consists of only one active element and one capacitor, and it includes one integrator and comparator. The behavior is obvious from these equations, and the duty cycle is 1/2. It provides triangle signal and square signal, and also in voltage. The second solution is only improved by this current source that serves as the duty cycle control element. As will be obvious from simulation results, because we simulated that CMOS structure with these parameters. This first graph shows the triangle and square response in time for some conditions, and the second graph shows the tuning range, because we are focused on tuning of parameters of these active elements. The tuning range is quite large. It starts from 5 and goes up to 10 microamperes. This is the current that sets the transconductance. These results are for the duty cycle that is 30%. and this graph shows the triangle. It was 1.2 megahertz, the highest GM available from the structure, and this is the square wave. Just for example, 70% results are almost as expected. And the second application is an PWM modulator that is based actually on two of these active elements, and we tried to sweep linearly and also by harmonic excitation, and also, as you can see, it works. Then we tried to measure it, so we had to prepare a behavior model because the silicon structure was not available at the moment. It looks really complicated, but it worked, and these are measurements results that prove the concept. These are particular results that show the tuning range in that configuration. The peak-to-peak range in case of square signal was constant during tuning process, and the triangle peak-to-peak range was linearly rising. And this graph shows that theoretical results and measured results are in good agreement in this range. This is not the conclusion because the works go on, and now we have it on chip. So this is the microphotography, but proposed and designed in different technology in I don't have it in CMOS 0.7 because it is much cheaper, and it is working very well. And these are some of the initial results because we have it only for a short period of time. So, for example, this is the tuning range of transconductance that goes to minus and plus values. These are several GM values versus frequency. And for example, this is intrinsic resistance tuning range, also very large. So one more slide. This is transfer. As you can see, for example, when intrinsic resistance is controlled by this current, minus 3 dB range is 18.5 megahertz, and so on. So thank you for your attention, and now I'm wondering if there are any questions.
Any specific question? Nothing. Okay, this session ends off here. Thank you for all the presentation and all presenters who contribute in this session, and for your support for attending this session. Thank you again, and hopefully we see you next year.